Welcome. I think we're going to have a few more people sprinkling in here, but my name is Erik. And
hi, I'm Mihai Parparita, and together we work on the Chrome Apps team.
So we're here to talk to you a little bit about the next evolution of Chrome Apps. So if, just as a quick show of hands so I can get a feel for what the audience is here, how many people are familiar with Chrome Apps as they are today? All right, great. That makes things easier. So why don't we dive in a little bit and just sort of do a little recap about how we got to where we're at today. So I/O last year, we talked about a few things. First off, as you know, we talked about Chrome getting to 160 million active users. We also launched for Chrome Apps in-app payments through Google Wallet. We announced that the web store was now localized in 42 languages. And we had the Angry Birds exclusive promotion that really showed how that it was really possible to make great quality apps just using HTML5. And we've kept busy over the last year since then. The first thing to highlight is Native Client. We launched that this fall. And Native Client really brought to the table great set of games. Some showed that you could do high-performance computing, that you could leverage native code in your browser. Things like Bastion, Mini Ninjas, From Dust, great titles that show off the capabilities of the platform. You saw Gaikai in the keynote today. That really was another example. We redesigned the web store. We had completely new look and feel, and that really expanded the usage that we saw out from our users. Users were much more engaged. They come back more frequently. They install more applications. We've announced today that we're up to 750 million app installs. Overall, things are going great for the web store. And of course, you know that Chrome is now at 310 million active users, almost doubling last year's number. So the reach potential for apps has been going through the roof. However, that's never enough. And we've been worrying about the platform itself and how to keep pushing that forward. And so we've been thinking about, well, what do web developers need? What are the capabilities that are missing from the platform? What can we do to move things forward? And so we've been listening to your feedback, and we've actually been bringing people onto the team who come from web development backgrounds, people who have experience building some of these web apps, like Mihai, who's our tech lead. Mihai was also the tech lead for Google Reader, which many of you may know.
So I was on Google Reader for quite a few years, and as you may know, Google Reader is an advanced Ajax-y application that has pushed the edge of what browsers can do. On the other hand, we felt like the platform could do more, could provide more flexibility, more power for Reader and similar apps. Just to give you a few examples, Reader was one of the first apps to be offline enabled. And that was a technical challenge. We fought with manifests and caches and like everyone else. But even once we delivered that, it was not the best user experience. Users had to enable offline mode. Users had to launch a browser to use the app, which sort of feels like a tautology. Why would I use a browser when I'm offline? Another issue that we faced in Reader was dealing with third-party content, where feeds can have Flash, they can have iframes, they can have arbitrary JavaScript, and we want to have the experience be as rich as possible, but we don't want a random feed to be able to steal your Google cookies or otherwise take advantage of the fact that it's being displayed in a privileged environment. We had to jump through a lot of hoops to sanitize the content, have whitelists, blacklists, and we always lived in fear of, well, what if we miss something? What if tomorrow anyone can access your Reader account and your Gmail account and all that? Finally, users wanted a lot more flexibility about how they consume feeds. Do they want to open up the item in a new tab, in a new window, in a pop-up? They want a mini browser inside of Reader. We couldn't provide any of that. We could provide a use window.open or target equals blank and sort of hope for the best, hope that the pop-up blocker didn't get us, but that was about it. And so Reader is, in some ways, a well-suited app for the web environment, and I'm sure others of you have run into even more issues.
Right. So we took feedback like that from Mihai, and we really started to push forward in terms of what we wanted to do. We're evolving in 4 main areas. The main one that we're going to start with is that we're pulling apps outside of the browser. Actually, we'll dive into each of these in a little more detail, but just the quick overview is pulling them out of the browser. We're enhancing the user interface, giving you more control over the windows. And we're making apps be offline by default, making it so it's easy to build them in a way that they behave reasonably when poor network connectivity. And finally, we're adding a wealth of new APIs to give you access to powerful system and device capabilities. So let's dive in a little more deeply. So what do we mean by breaking out of the browser? Well, the first thing we mean is that you launch apps from outside the browser. So you'll see in a minute here that basically you'll no longer need to go launch the browser, go into Chrome, go to the new tab page to find your apps. The apps will instead come from the operating system, the traditional place that you're used to finding them and launching them. Second, the apps will act as peers to their other native applications. Top-level windows, they interact, Alt-Tab to switch between applications. Everything you'd expect a native app to behave like from a user interface perspective, OS integration perspective, it will no longer be a tab in a browser. So let's give them a demo and show them what this looks like, Mihai.
Sure. So this presentation is actually itself an app. So the demo button just breaks out of the app. And if I move the window out of the way, you can see that I have my top-level window. It has minimal, no tab strip, no Omnibox, and there's a Chrome icon at the bottom that seems to be getting clipped, and where I can make tabs, and the application itself has its own icon in the launcher. This is the experience on Chrome OS, where there's a full application launcher. On Windows, there'll be shortcuts on the desktop and the appropriate behavior on other platforms. So let's switch back to the app.
Right.
And let's talk about UI.
Right. So the enhanced user interface. So you already saw that it has a native level, top-level window frame. There's no browser Chrome. There's no tabs. There's no address bar, no back button. And further, you have full control over the look and feel of that frame. Next, you can actually manage multi-window applications. Actually, I did this the wrong order. So, multi-window applications. So that means you really be able to cooperate between multiple windows and have them interoperate. Today, in tabs, it's very hard to sort of have multiple tabs that are cooperating with each other and interacting with each other. And it's hard to do things like toolbars and panels that cooperate and interact with your host window. And one of the things by not having browser Chrome is, well, what do links do? Well, links behave just like they would in a normal native app. When you click on the link, it opens the browser window. Let's show them. So there's a link to google.com, and
I'll tab back to the application.
Right, and so now you're back inside the application. So we've got another demo here that shows a little bit more about what windowing control can do.
So this is a little toy demo showing that we have an app window, as you can see, the minimal Chrome, and the Bizarro World one is actually a full custom window where the app controls every single pixel on it. In this case, I just made it all black. We have full control over behavior, so I can have it resize itself, certainly drag around and follow. So you can imagine this could be a little dock toolbar, and I can control other aspects of the window like minimize state.
Right. So offline by default, before we dive into the specifics of this, it's probably worth explaining what do we mean by offline. So a lot of people think offline, they think, okay, I'm on an airplane, I have no connectivity whatsoever. But that's not the only time that offline matters for applications. Offline can mean I have got slow connectivity. I've got spotty connectivity. For anyone who uses a cellular network, maybe in this building, Wi-Fi, you're used to not having reliable connectivity. The speed might change as you go. Maybe you're in a hotel with a captive proxy. If your application is trying to talk over the network, it needs to be able to be robust in the face of these different network connections. So how do we do this? Well, we're starting from a base of Chrome packaged apps. Basically, for those of you who are familiar with Chrome apps in general, packaged apps are a zip file, a collection of HTML, JavaScript, and other resources for your web application that are downloaded, installed on the user's computer. So all the code and logic is always there, ready to go. We take some extra steps and to make sure that we're enforcing a strict separation between data and user interface. By being packaged, by making sure that all the code and logic are always running from the client side, not being generated server side, we mean that the app doesn't get into a broken state. And it's up to you to to download your data, store it locally, render your UI appropriately. We further enforce this or support this with building APIs that are themselves resilient to being in these poor network connectivity conditions. And finally, this may seem like a small thing, but the fact that we've moved apps from launching outside the browser actually addresses one of the key usability issues with offline. Today, some of you may have actually gone through the effort to make your hosted web app work offline and found that even after you went through all the effort to work with App Cache and to make that all do what you wanted to do, that users were still not finding that functionality, and they were still frustrated using it. For the reasons that Mihai was pointing out before, they had to know first to launch the browser. Then they had to somehow navigate to your app. Well, if they know how to bookmark it, that's about 10% of users, then they can get back to it. What about for the rest of the users? Well, for them, they have to either know what the URL is ahead of time, or for many of them, actually what they do is they go to their favorite search engine and they try to navigate to it. And guess what? When you're offline, search engines don't really work. So people, when they're in a poor connected world, are continuously reinforced that the browser doesn't work because all their tabs are broken. They don't know, even when they have an app that they know works, they don't know how to get to it. So pulling an app outside the browser and making it a first-class peer to their other native applications gets past all that anxiety and all of the logistics of getting to there.
So we're going to demo this quickly, and we're going to get the presentation out of the way. I'm going to yank the Ethernet cable out of my Chromebook. As you can see, there's a little icon in the corner that says I'm offline. I can refresh Google and show that it doesn't seem to work. And we're going to install an app. In this case, we're going to sort of do a kind of a stress test where we are offline. We're going to install the app right now in developer mode, but the installation process is the same. And this app has never had a chance to run before. It's never had a chance to talk to its server, download data, but the experience should still be acceptable. The specific app we're doing is a diff tool that lets you compare files. So when it launched, it has an offline indicator that says you're currently offline. So all it can do is it can diff local files, but that should keep working. So let me just pick a couple of files and diff them. And as you can see, I lost focus. As you can see, the application still works. If I manage to find the Ethernet cable and plug it back in.
Right. While Mihai is doing that, I'll point out that this is, we're doing this demo on Chromebook, and we're doing it with the latest Canary build of Chrome OS. So we're taunting the demo gods, and
but in this case,
they got us back here a little bit.
So we are back online. The app has noticed that we are online. The choose URL feature has appeared, so now we can diff not just local files, but ones that live on a server. So I think I have some shortcuts set up here. And as you can see, we are fetching live URL.
Right. So this is really a torture, case for an application. It launched for the first time, never having seen the network. So it was able to run robustly without quitting and relaunching it. It recovered. So it was able to see, the fact that the network was back. You didn't have to do anything. You didn't have to refresh the page. You didn't have to take that extra step. The app was just able to proceed.
Now that the projector has been fixed, you guys can see that the app launcher at the bottom is what I was referring to, where all these apps can be launched from offline.
Right.
So back to the presentation.
All right. So new APIs. Now, this is one of the area that I think most of you are going to dive into first when you start playing with Chrome packaged apps, and is all the new APIs. We think of them in three groups. The first area are what we call system APIs. The system APIs interact with the operating system at a low level or with hardware on your device. So maybe USB or Bluetooth or as you saw in this morning's keynote, raw UDP or TCP. These will enable a wide variety of apps that you've never been able to build with web technology before. Next, we've got shared data APIs. And shared data APIs are provide ways of interoperating with other applications on your system. Things like photos or contacts, calendar entries, things that you want to be able to access safely from multiple applications. And finally then, a group of service APIs. The service APIs are the web services that you all know and love, but built into Chrome, into the Chrome runtime in such a way that it's going to be resilient to poor network conditions. So things like analytics, in-app payments, ads, maps, things like that will be coming to these APIs. So why don't we give a demo of one of these APIs in action?
Sure. So this demo is going to display me because I'm going to hold a physical device here. This is a little science fair kind of project that one of our engineers, Mike, made. It has an Arduino board on the back. It talks to the Chromebook via a serial port, or serial over Bluetooth, a serial over USB in this case. And it has a little stepper motor here that is controlled by the Arduino. And this slider at the bottom of the screen controls the motor. It just sends a 1-byte command saying, please rotate to my current position. And that goes over the serial wire. The Arduino interprets it. The key thing here is that the Chromebook knows nothing about this particular device or about Arduino in general. It just knows that there's a serial port, and that in turn is exposed to the application. So all of the logic about the specific device is in the application that can be installed by any user.
The other key bit is that all this code is just JavaScript and HTML, right? There's no special, no device drivers, no native code that really needed to be there. That said, we are going to be providing bindings to, in addition to JavaScript, also to Dart and to native client. So you'll be able to access these APIs from whatever programming environment you'd like. Speaking of the programming model, why don't we dive in and take a look at some code. Before we do that, though, just a refresher, what is behind the core bit of the programming model. So as I said, these are packaged apps. And that means they're a directory full of resources. They have a background page that acts as a hub. What that means is this is what starts up. When you launch the app, a background page launches, and it triggers an event. And then it's up to you to decide what to do. In previous incarnations of Chrome apps, we had a launch URL, basically a page that would open up in a tab when you did. Now you've got full control over how your app behaves, how many windows it opens up, if it even opens up a window at all, or maybe does something in the background. And that last step is sort of an important use case that we're really interested in, is being able to handle system-level events and have your app come and go based on signals from the runtime. So let's take a look at some of the code that shows this in action.
Sure. So I'm going to code up a Hello World demo. And incidentally, to actually code the app, I'm going to use an app. This is a text editor that's been whipped up by one of our other engineers. So like Erik said, first we start with a manifest. So if you went to the extension talk yesterday, you know that there's a new manifest format called manifest version 2.
Right. And manifest 2 basically is the trigger that we use to enforce some of the new policies with apps and extensions. It turns on CSP by default, which we'll talk about in a little bit, but it also is one of the keys for showing off the new app behavior. It also has the basics that you're used to, a name, a version, and another field that you've seen before, the app field, but rather than a launch URL, like we said before, instead it has a designation of the background page. As I said, the main, the hub of the application. It uses the same event page technology that we've just announced with Chrome extensions, which means that it basically can come and go on demand as the system needs it. So we've specified the app. The other thing, actually, Mihai, you might want to add permissions to it. So permissions are the way of specifying in the manifest what capabilities your app needs up front. This allows us to control it's a security feature that basically allows us to limit the damage that an application can do if it has a bug in it. So then, next we're diving into the actual background page itself. So this is main, and as I mentioned before, what it does is it loads, and then it fires off a launch event. So the first thing Mihai does in his background page is set up an event listener for the background page. And in that, first thing he does is to create a window using our new app window API. And basically, this is the hello world. Launch the app, get a launch event, create a window, display some text. We're going to show just a little obvious snippet of HTML. So here's our hello world. And then the next step is to load into Chrome. Now, again, since this is just a packaged app directory, it's built in the same technology at Chrome extensions, and other Chrome apps have been built in the past. So just going to the Chrome extension page, going into developer mode, load an unpacked extension, and then we can just launch the app from the app launcher directly. And there you go, we have our hello world. So really trivial bit of code, but as you could imagine, we could do whatever we want from that launch event and do more advanced things. So before we do the more advanced things, let's talk a little bit more about some of the other features of the programming model. So one of the things that's interesting is that all of the windows are what we call single-page applications. There's no navigation. So we think this leads to an overall better experience and simplifies a few things. Again, the fact that we don't have a back button, that we don't have an address bar, we don't want to have people building apps that wind up getting users trapped and stuck. We want to get rid of that flash of white repaint. And we've also actually removed a few web features, things that are that we think lead overall to bad web performance or have security problems with them. It turns out that on the web at large, it's very hard to deprecate features, very hard to remove things. We have strict compatibility needs. As people who are going to be building these Chrome apps are going to be starting from scratch, we have the opportunity to take a few and just eliminate them from the beginning. And there'll be things like synchronous requests that would block the UI thread, or again, things that might cause security problems. Speaking of security, let's talk a little bit about the security model. So to start with, you get all the things that you're used to with Chrome. You get process isolation. Chrome is famous for being a multi-process browser, and apps are no different. Each app runs in its own process, completely separate from each other. We also sandbox each app. So each app has its own storage area, its own sandbox execution runtime sandbox, which makes it so that even if it had a bug, the damage to what it could do is tightly controlled by the runtime. And part of that is the permissions model I was talking about before. The app has to declare upfront what capabilities it wants to use. So in this case, we have our little app that used the serial port API and the webcam. So if that happened to have a bug in it that could be exploited by an attacker somehow, the worst that could happen is it could do exactly what that app could do and talk to the serial port, the webcam. This is very different from what you're used to with native executables, where once you have a security bug in a native executable, you have access to the whole machine. Everything the user could do, an attacker can do. So I mentioned content security policy. Now, what content security policy is a way to protect your app against cross-site scripting bugs. For those of you who aren't familiar with cross-site scripting, it's basically a way that an attacker can somehow get code injected into your page and run in the context of your page. Now, in a web page, this is bad enough because it means, like in something like Gmail, it could, an attacker could maybe read all of your email and post it to another site. In the context of an app, it could do even more potentially with the new, more powerful APIs we're adding, like, I don't know, again, access your webcam, leave persistent files somewhere on your hard drive, talk to some hardware that you didn't want them to talk to. So we really try to lock this down, and content security policy makes it so your apps will be resistant to these sorts of attacks. So let's show that in action.
Sure. So I'm going to take my Hello World demo from earlier and make it actually do something besides display Hello World. I'm going to have it have a little form that asks the users for their name and then displays it in the output. So that's the markup side. And then on the scripting side, I have sort of the obvious implementation of what I just described, where I where I get the submit event and display the name in the output field.
For those of you who are, the more observant in the crowd, you'll know that inner HTML is a pretty dangerous feature of the web to use. It basically is he's taking unescaped content and just injecting it as code straight into his page.
So actually, before demoing it in the app, let's load that same page because it doesn't use any app APIs, just in a regular Chrome tab, the way a web app would run in. So sure, I can type in my name, but because of inner HTML, as Erik mentioned, markup gets interpreted, which H1s aren't so bad, but well, what if I had a on-click handler here that...
So you can see that this is script. He's actually typing in JavaScript that now is going to get injected into his page. Now obviously, this is a very simplified form of an XSS bug because there's a form field and the user had to type it in. Usually, they might come in as a parameter in a URL or read from a database that they somehow got data stored into your system. But you can see that if they could run code in the context of your app, they'd be able to do the dangerous things that your app can do. But let's try that same code in an app.
So app still works. HTML still gets interpreted because Chrome does what it's asked and it uses inner HTML. But if I type in that same script snippet, and try to run it, nothing happens. If I pull up the developer tools, so these are the same developer tools that you're used to, you can see a content script policy error that appears.
Right. So this basically is showing you that we are locking down the app. So if you have a bug that might enable somebody to inject inline script into your page, it can't exploit anything in your app. It's just stopped right up front. As Mihai pointed out, this is all tightly integrated again with all the developer tools that you're used to, so you can leverage all the power that's there. They've been evolving really rapidly, and so there's a lot of great features if you haven't been checking them out. So let's talk about a few other bits of the security model. We take a further step and isolate storage from one app to the other. So what this means is that what gets written in one app, what happens in one app stays in that app. It can't affect what happens in the other. Cookies in your browser don't affect cookies in your app, and vice versa. And this is true not only for the origin, but if your app is interacting with web content from other origins, that too is isolated. So if you're logged in to Twitter, in your browser with one account, and your app interacts with Twitter, it isn't affected by that. It would have to log in separately. And I mentioned explicit shared data APIs before when I was talking about new APIs. This is also a security feature because it means that we can give apps access to more powerful functionality without exposing your whole hard drive to them and without giving them the ability to write arbitrary files into arbitrary locations. So they can't leave an executable on your hard drive, and they can't just read your Quicken file, for example. But they can read your photos, perhaps, if they've got the photos permission. And one further distinction that we've made for apps is that we no longer have access to extension APIs within packaged apps. So we made an explicit split to say that an app is outside the browser, and that means that interacting with the browser through these extension APIs no longer makes sense. It's also true vice versa. Extension APIs can't affect apps. These apps are truly isolated from the browser and operate on their own. There's one last security feature that we added here, which actually has some very useful functionality as well. So you've heard us just talk about how we've locked down this and locked down that, and you can't get this web content or that content. Well, sometimes it's actually really useful to get hosted web content into your app. Well, in a similar way that you're used to with native desktop and mobile applications, you can embed essentially a view, a full browser inside of your app using something we call the browser tag. So this is different from an iframe in a couple of different ways. The first is that it's a top-level frame. It doesn't think of itself as an iframe. It thinks of itself as if it were in a tab or in a window by itself. Second is that it runs out of process. So if there's a bug, if there's some issue where by going to a remote website, somebody found a security hole in Chrome, it would only affect the browser tag instance. It wouldn't be able to affect your app. And finally, once again, storage is isolated. So again, what happens in this browser tag doesn't affect what's in your app, and vice versa. So we've got a little more time, so why don't we dive back into that serial port demo and show what it's like to actually use some of the more powerful APIs and to do a little bit more stuff with it.
OK, so I'm going to close some more windows and load up a standalone version of that serial port demo that we had earlier. And let's launch it. So same sort of setup, camera using the WebRTC API to show me, the same slider. This one's a bit fancier. It has a serial port picker listing all serial ports that are local. So the goal is we have a Chrome logo, physical Chrome logo here, and we have the on-screen Chrome logo here. This board actually also has a potentiometer, this little knob I can turn. And I want to make it so that turning this knob turns the logo on the screen. So let's pull up the code for this. So it's in servo. And
right, so the existing code was basically writing to the board, sending it data. Now, this one, we're going to change it to add a read function, read back.
So walking through the existing code briefly, we have the WebRTC side of things where we get access to the user's camera and display the result. Since the app has the video permission, this did not trigger an info bar. The access happened immediately. We have the slider, the HTML5 range element here. We set up an on-change listener for it to set the position. And we build a serial port picker by listing all of the ports that are available. Once we pick a port, we have the open API call to actually open up a connection to it. And once we open, we can start setting the position. We have the connection ID that we get from the API callback. All these functions are async, and we can start setting the position. To actually set the position, we just send a single byte as an ASCII character from 0 to 9. We're using array buffers so that the serial port API can work with any kind of binary data too. We're using ASCII here for convenience. So as Erik mentioned, the next step is to actually start reading back from the board. So given that there's a write API call here, because you can imagine there's also a read API call we can use.
Right. As Mihai mentioned, all of the Chrome app APIs are asynchronous, so you'll notice they all take a callback. And so he has in his function there an on-read function for the callback, which he's just pasted in to save some typing time.
Yep. So again, it's also using array buffers. We read back the data from the serial port. We do the opposite conversion from ASCII to a degree value, and then we use CSS3 transforms to set the position of the logo. And finally, we want to read the next byte. So this isn't a blocking call. It's just whenever the next byte happens to appear, the callback will be invoked again. So let's save this, and we're actually going to save it in the same place.
Right, and that, by the way, that programming model did show some of the flexibility and power of having an asynchronous API. Is that we're able to sort of queue these things up and have multiple, async things going on at once, and the callbacks happen, when they happen. We don't have to worry about interleaving them.
Okay, now back in the app, it's the same sort of edit reload cycle that you might be used to from web development. And so let's make sure it still works, that we can still control it, and so that part still works. And now if we have the knob up here and we turn it, the Chrome logo appears to spin. So we're reading data.
Now, obviously, this is a really simple demo, and not all of you are going to be sitting in your garage hacking on Arduino boards, but we're hoping that this sort of conveys the kind of thing that you can do, all using web technology and interacting with hardware and system-level data.
Yeah, for example, people on our team have built IRC clients, Telnet clients. They use the raw socket API. Someone else built a interface to a heart rate monitor that uses Bluetooth. All of this works on a Chromebook, for example, that couldn't talk to these devices before.
Right. So let's sort of wrap up about and recap a little bit of what we've gone over. So we're evolving apps to break out of the browser, to have enhanced user interface, more control over the windowing, to be offline by default, to have access to new, more powerful APIs. Now we're also, this is also available for you to play with right now. Basically, as we said, this is a Canary build of Chrome. For those of you who don't know, the Canary is our nightly update schedule. It's available for Windows and Mac. If you're a Linux or Chrome OS user, if you're brave enough, you can do your own build, or you could wait a couple weeks for our next dev channel to come out, and you can start playing with it then. We've also been asked in the past about why are these apps, specific to Chrome? Why are they tied to Chrome? And part of the reason is because, well, there hasn't been a lot of appetite in the browser community for doing things or doing more dangerous capabilities. But in the last 6 months or so, we've been talking to more and more folks from the community and discovered that momentum had been building, that people were all starting to think along these same lines, that using web technologies to build more powerful applications, its time has come. And so we're working with the W3C and with other browser vendors, including Mozilla and Adobe and Intel and Samsung, people in the web community, to form the new working group to help standardize this going forward. So we're excited to help take the technology that we've been building for Chrome and try to contribute it and make it a standard across multiple operating systems and platforms. And finally, you heard Sundar mention this in the keynote, but our intent is to make these apps work on mobile as well. Everywhere the Chrome runtime exists, we think that we can bring this technology along with it. Now, we only showed you this very simple serial demo, but there's a lot more that you can check out. Some of it right here at I/O. If you go over to the Chrome Sandbox area, for example, you can see Sencha has a neat media player demo that actually is implementing UPnP to stream from a local media server, which is kind of cool. Kendo has a photo booth app that uses a lot of the WebRTC stuff. There's a text editor that was done by the AngularJS team at Google. And there's a demo that we'll call Johnny that is
Johnny HTML5.
Oh, Johnny HTML5, sorry. Johnny HTML5, which is a LEGO Mindstorms robot that's being controlled over Bluetooth from your desktop computer. Now, you can find all of these samples and a bunch more, actually, in our new GitHub repo at github.com, Google Chrome. There's an apps demos section there. So I encourage you to go fork and play and contribute. And finally, the way to learn more, you can read our docs up at developer.chrome.com/apps. Now, just a quick warning, since all of this is new on the Canary channel, by default, our apps documentation points you at our current stable channel stuff, but there'll be a helpful link.
It's been fixed.
There'll be a helpful link there that shows you how to get to the latest stuff. You can also join our mailing list, Chromium Apps at chromium.org. And if you want to talk to people in person, people on the engineering team, we also hang out on IRC on Chromium Apps at Freenode. So feel free to join in and ask away. We're looking forward to hearing from you. We're really excited to see the kinds of things you guys can build with what we're doing. But it is early on. Expect some bugs. Expect some growing pains. We'd love to hear your feedback. So now we'll take your questions. So if you have any questions, please come to the mic. By the way, if we end this and you still have questions you'd rather not ask at the mic, we'll stick around afterwards for a few minutes, but also you can find us over at the Chrome booth. We'll be having office hours, so feel free to not only check out the demos, but come by and ask us questions. All right.
Can an app launch another app?
Not right now. It's a good question.
Well, can you describe more specifically what you'd like to do here? Like, is it a matter of like, I want to send an email, so I like to launch the Gmail app kind of thing?
Well, sort of like the launcher, but without having to bother the user with them going to find the app, saying this is the app that you're looking for to complete this request.
So you can do some of it with web intents, but not exactly the way you're talking about for making a full launcher replacement. But that's the kind of thing actually we would probably more likely expose through extensions in some way. But remember that each operating system is going to have its own sort of natural way of launching apps. So even if we did provide it, that might be specific to Chrome OS or something like that. Go ahead.
Yeah, you mentioned early on the presentation about offline usage and the APIs into the system that would degrade gracefully when offline. Can you give some examples of that?
Sure. So take, for example, something like Google Analytics. Right now, everyone's used to using Google Analytics in their app. They want to see how their app is being used. And the way to traditionally include it would be to say script source equals, whatever, path to, your analytics JavaScript file. But what if you're offline? So first off, if you're offline when you launch the app, it might just fail to load the analytics code altogether. Or it might load part of it, not all of it. Then let's say that you load the code successfully, but then go offline. Well, the traditional way that it does its thing is to ping a server to send its data. So in that case, we're modifying both the API to be loaded, safely, always on the client side, and to know when it's offline and to store and cache some of its statistics locally so that it can save them up and report them up at a later time.
Okay, thanks.
So you said there's going to be a split between the app extensions, the app APIs and the extension API. Can you tell us a bit more about these, which go into which category?
Sure. In general, extension APIs are going to be limited to the things that affect the browser, that affect web pages, tabs, that sort of thing. And apps is going to be, everything else. Now, there's going to be a few that are going to exist in both. In general, what we've done is, for now, limited the ones that are more dangerous system-level things, and those are not going to be available in extensions to begin with. It's something we're evaluating. We might change our mind on some of that over time. But to start with, we're going to try to keep a clean break between those sorts of things in apps, and the things for extensions, keep those tied to things that affect the browser.
And some APIs might behave slightly differently. So the context menu API, for example, can affect any web page, but when used within your app, it would affect only your own app's pages. So the docs, I think, should cover this, or we'll start covering this. Okay.
You mentioned the app can use a browser tag to launch another website. So can any JavaScript in that website interact with the app?
Sure. The way that it'll interact, you can interact with the browser tag, but it'll be through a very specific post message type of interface. So it will be possible to have some hosted web content that you want that can message out, and for you as the embedder of the browser tag to inject bindings into the page as well. So you'll have full control over that page. We actually expect eventually the API to be rich enough that people will be able to build a browser using the browser tag. So maybe you don't like Chrome's UI and you want to build a browser with tabs on the side or something, I don't know. We think that eventually you'll be able to do that with the browser tag.
What is the level of integration with the file system? So I saw in the text editor, you click open a file, it gives you the browser and you pick a file, but say you wanted to build an editor where you have, a directory tree on the side like a normal ID
Sure.
and click through it. Is there some, what kind of APIs are available for accessing the file system generally?
Right. Actually, good point. We didn't mention that, but probably most of you noticed that the text editor we were using is itself an app and was interacting with the file system, and that text editor is using, was all JavaScript and HTML as well, and it was using some of the file system APIs that we're working on. In general, we're trying to limit it. We could think of file system access in kind of two ways. One way are ways where the user specifically indicates a specific file that they want to give you as the app access to through a standard open save dialog type of thing. For that, you can access files anywhere on the system, have read-write access to them with the right permission, that sort of thing. But in terms of arbitrary non-user initiated things, or things where you might say, oh, because of file A, I also want to access file B, C, and D, we don't allow you to do that. And so in those type of cases, take an IDE example, for example. We would say that you should build something that interacts with files in your own sandbox in that world. And so in that case, maybe you might use native client to build a Git implementation that actually can directly pull down code from your repo right into your sandbox and edit things locally there. In your sandbox, you've got full access to all the directories, all the files, unrestricted. It's the rest of the hard drive that's off limits, unless the user does a specific gesture to get granted to you.
The third way for getting access to other files on the hard drive is via these shared data APIs. So if your app is interested in not any arbitrary file, but photos, then it can, yes, ask for any photos without a user gesture.
So does that mean like so for example, on a Windows or Mac system, there's like a system photos directory where supposedly the user puts their photos. You can ask for permission to access the files in that directory. Is that the idea?
It's not exactly that. It's a little more. So we'll actually try to discover the types of places that you that you store your photos. And so a lot of people don't keep their photos leveraged to that one thing. They've got an external hard drive, whatever. There'll be the ability for users to configure what defines their photos area. But even then, it's not just directory access. It's also we limited to the types of files that you can access to. There have to be known types that we expect to be photos in that case.
Right. Okay.
Are there any particular patterns or practices that we should employ when designing apps in terms of UI state? So when a user exits a UI, we want that UI to come back like exactly the same as the user exited.
Yeah, exactly. That's a good point. So there's a lot of things that that I think are going to change in terms of how you build these apps that are different from what you might expect with a web page, because you might be dealing with multiple windows, and because your app can get shut down and pulled back at any time. We definitely want you to be resilient to that and to be able to restore and pick up from exactly where you left off in those cases. The example is, think about this, that these apps also need to be able to run in mobile environments where mobile apps don't have guarantees of lifetime, right? So that means that you have to write your apps in a way where they might be shut down due to system resource issues, right? But the user then switches back to them, and it should look like nothing happened. It should look like you never exited.
The other part there is that we have a storage API. So for storing of the state, you can use a storage API, which looks like local storage, but is asynchronous, and more importantly, is synced. So your app can have the same state across all Chrome devices that the user is signed into.
Yeah, absolutely. So we actually think it's a really interesting use case that you have your app in one state, on your machine at work, and then you go home and you launch it again, and it can pick up from exactly where you left off at work.
And is there any ability for external devices to wake up apps?
Well, basically, the whole gist of this notification-based model that we've got for the app, it should enable that sort of thing. We don't have any specific APIs to talk about on that front yet, but absolutely, you can imagine things like server push, synchronization, that sort of thing will all be the types of things.
I think the one thing we have is for the media gallery API, if an SD card is inserted, it will fire an event, for example. So your app can decide to do something in response to photos that just appeared, even if it's not running.
With the serial device that you were working there, when can we expect support for USB devices in Chrome, and will it cover the whole range? Can I have a device that emulates an RS-232 system? Could I access these kinds of things with Chrome, through Chrome?
So this serial device here was actually over USB, so it's serial over USB. And actually, we do have a USB API as well.
That's a low-level USB API. So.
Right, exactly. So basically, if you know everything about a device, one of the demos that we have, and if you look in our repo, is for a specific...
It's a Griffin PowerMate. It's a knob that senses rotation position over USB, and we can read it, byte off of it.
Right. So there's a little bit more work we need to do on the USB to really flesh it out. For example, we don't have support for HID devices yet, and I think it'd be nice for us to build in a little more knowledge about some of the specific devices. But right now, it's low level. You have to know a bit more about the device that you're talking to.
But for example, one of our developer relations people has gotten his Kinect hooked up to an app, so that seems to work.
Time schedule, approximately, months, years?
Well, as we said, you can play with this today. And you know that in general, our approach is to take a very incremental, release early and often type approach. So our intent is to get it out this year, into the stable channel. But you should be able to start playing with it now and building apps now. It just depends on your tolerance for early code.
Right. Thank you very much.
All right. Well, we might be out of questions. Any others? All right. Well, I think that's about it then. If anybody wants to find us afterwards, like I said, we'll be over at the Chrome booth answering questions, and come check out Johnny HTML and the other fun demos over there. And hope to hear more from you. Thanks.